Yeah, no, but okay. So the way that I'm gonna teach today, the script that we're making should be able to apply to any geometry ever. Okay. So. Yep. So basically, the thing is, I could probably actually teach this without a hyperbolic paraboloid. So, but maybe I will. So there's a few. I think if this is ending up in any other class as them watching it, I just need to have everyone understand that the like Julia's class and Christina's class may be doing this a little bit differently. My intention is to teach you a way that can apply to any geometry, as long as that geometry is a solid. Okay. So a lot of you guys haven't made solids. We've just been making surfaces. So a quick and easy way of making it solid is by extruding it. So if we've got this hyperbolic paraboloid, I can take it, run it through an extrusion. So here we go. We get that, give that a vector of z, and that's now made a solid. If you do that with a B-rep, like the sports hall, that'll work. So as long as you might have to join it. So if you've got two hyperbolic paraboloids, you may have to run them through. Let's actually do it. If we just plug them straight into a extrude, one of the major problems here is we're currently dealing with two B-reps or two solids, and we technically need them to be one. So a quick and easy way of doing that is by actually joining these together before they go in. So we can do that with a B-rep join. So as that goes in, we should only produce one closed solid B-rep. Or the other way is if they were to go into the extrude, then we can run a rather computer intensive function called Boolean, which I will explain a bit later. But if we run a solid Boolean, that'll also produce a solid B-rep. But let's just do the join one. So that's mainly for these guys, or anyone who's sort of, if you're working on something that maybe is made up of two hyperbolic paraboloids, you might want to actually create a waffle system for both of them, like separately instead of all at once. So it depends. Like for example, the radial system that we've been working on in class, you might want that waffle to change orientation as it rotates. So you know how we've been making sort of one shape and rotating it around. Then I guess the benefit here is we can just waffle that one shape and then make 6 of them or 8 of them or whatever. Cool? So I'm just going to stick to one hyperbolic paraboloid at the moment. So we've been we've been producing a lot of really complex geometry over the last few weeks, and it's round about now that I would actually expect you guys to start producing things with planes. So congratulations, you've proven that you can be more advanced earlier on. Good job. Sorry. Sorry for pushing you that hard. So what we are doing is we are producing a waffle, and let's go lamp, just to prove it. Up. So waffles are effectively taking geometries that may not necessarily be capable of being made with planar objects like timber, and we are basically analyzing the geometry and getting planar elements out of it that we can then laser cut, for example, or CNC mill or whatever. And the critical thing is we don't get the surface as an outcome. What we get is something that the mind's eye can see as a surface. So we can all see here that this is not a sphere. I can put my hand through it, and it's made up of these planar objects. But you look at it with squinted eyes, it's a sphere. You can roll it down a hill, it will roll down the hill. Yeah? So the critical thing here is the stuff that Christina was talking about last week when it comes to, is a surface developable? So is that we can actually start taking surfaces that are developable and make them waffles, because what helps define a developable surface? Yep. So if I were to pick a point on it, could I draw a straight line through that point and it would go through the surface? Yes. Okay, so I can take a cylinder and I can pick a point on the cylinder and draw a line through it, and that line will be on the surface the whole way through, right? So that means perpendicular to that, line, there is a circle, yeah? So the really nice thing about waffles is that they don't necessarily have to be orthogonal as a system. So they can be radial, they can be conical, as long as the intersection between one section and another is 90 degrees, then you've got a fairly safe bet that it's going to work, right? So do you feel like I could waffle a cylinder in a similar fashion to this lamp? Okay, so if I were to take a cone and waffle it in these particular directions, it would probably work. Okay? Probably. Yeah, probably. Depends on which direction you go. Okay, so what we need to do is we need to start defining some elements that cut through our geometry in a planar fashion. What types of geometries are we dealing with here? We've got a solid B-wrap, solid surface, a series of surfaces. And what else do you think we would need to generate the waffle? Planes, right? So, and we've done this already. We've cut planes through objects. What were we cutting planes through last week? No. Oh, yeah. So we're cutting them through parabolas and curves, right? Through circles and lines, yeah? And what was the outcome? So if I were to put a plane up and I were to run a line through it, what would the outcome of the intersection be? Oh, a point. A point, okay. So if I were to take a plane, let's say that runs in 3D into that cylinder, what do you think the intersection of a plane and a solid would produce, or a surface? Or let's say surface. So let's say this is an open cylinder. What do you think the outcome would be with the intersection with this and a cylinder. 2 lines? Yeah, I'll draw them in. Whoop. Whoop. Yeah, 2 lines. And if this was a solid cylinder, what would it produce? A surface? A plane? This is a plane.
Section.
Yeah, so, well, yeah, it would produce a closed curve. Yeah? Like, I know, like, yeah, you're right, surfaces are technically closed curves, but yeah, it produces a closed curve. Cool. Okay, so if we've got a surface or a B-rep, a solid, then we should be able to get a curve that intersects that with a plane, okay? So the instructions required to start making something like this with the laser cutter and assembling it just requires a B-rep, a solid B-rep, and an array of planes that are effectively oriented in that manner. So then the third point, and this is one that Christina made quite critical, if I were to take a second plane, like so, and cut it through this cylinder, like so, and we were to make this now out of wood, what is the issue? So these two shapes end up looking like this in the laser cutter. So when we go to put them together, what's our problem? Yeah, like wood can't exist in the same space as another piece of wood. So the typical solution for this is to put a slot in one and a slot in the other. So let's say that's 50%. Sorry for my poor drawing. So if you were to put a slot in that meets at halfway, or if that slot were to go to 20% and 80%, then when these two pieces slot together, the material that is in this zone and the material that is in this zone do not collide with each other, and therefore the piece will fit together, okay? And they'll come together literally lining up to make a cylinder, yeah? Okay, so can you see that, like, we're probably not gonna go through a full pseudocode at the moment, we're just gonna step through it, but what do you feel is what do you feel is the first step now that we have a solid? Planes. We've got to start defining planes, okay? So another issue that is going to come up is which direction do your planes go? Okay? So when I have a waffle, let's say I'm looking top down at my waffle, when I have a waffle like so, where the material is flat and planar, and it's got a thickness. When I have, I'm going to draw this really big. When I have these two elements slotting together, it is very easy. You're doing this in easy mode, basically, if you make them 90 degrees, okay? Because what happens is you just have to knock out the material in one and the material in the other, and when they slot together, the two surfaces and the process that you're using to actually cut them will force them to be 90 degrees, yeah? So if I tried to rotate this in either direction, the board, the material on this vertical material is preventing it from rotating, yeah? But if we were to try and make a waffle, can everyone see? Can you see that? If we were to make our waffle orthogonal, making it a diagonal waffle, and it's possible, then the material, like because we're using a laser cutter, right? What direction can the laser cutter only cut in? Vertical, down, the z-axis, right? So if we were to cut this material, we would only be able to cut it vertically. So for it to not clash with our other piece, it would need to be cut there and cut there. And the same applies here. It would have to be cut there and cut there. Yeah? And the problem with this now is when these go to slot together, does the material force the elements into a shape? No. I can rotate this now. This can rotate all the way to that point, right? So it's not necessarily, you're not making it easy for yourself to do that. So this is where deciding the direction of the planes becomes really important. If you've got a hyperbolic paraboloid that isn't a square in plan, like it looks like this, right? If we were to draw lines through it, they don't end up becoming orthogonal, do they? So you're making life hard for yourself for this particular assignment, yeah? Okay, so we want to make sure that our planes are orthogonal for now. If you want to make life difficult for yourself, you know, get yourself a little bit of a boost in points, like assignment points, mark, whatever, then yeah, go for it. Absolutely go for it. Love to see you work it out. But for today's class, we're going to go through orthogonal. Cool? So with the hyperbolic paraboloid, if I were to draw these diagonal lines diagonal planes through, what is the likely outcome if we use the 4 points? Like, what's the likely outcome of the curves? They'll be what? Was that someone talking? No? Okay. There'll be lines, right? If you have a point over here and a point over here and you draw across, like dividing equally, will produce a straight line, yeah? If I were to do the opposite, if I were to take a hyperbolic paraboloid and cut it in these directions, what are the curves that we're going to get as a result? Think back to last week. Parabolas, yeah? We're guaranteed to get parabolas, yeah? So if we were to start cutting this orthogonally in X and Y, we'll get parabolas, yeah? Definitely. And that, I think, is the intention that Christina wants from a lot of you guys, is that you are doing something that's orthogonal or to the topology of the hyperbolic paraboloid. But what's really interesting about these types of geometries is you would consider that rationalizing it, but if you're cutting a plane through it and you're using a laser cutter, does it need to be a parabola? No. Does it need to be a straight line? Like outcome? Does it need to be just a bar? No. It could be any shape. Yeah? So like the laser cut animal decoration. These are not parabolas, okay? These are whatever shape you want them to be. Please don't tell me that someone somehow breaking through my... Okay, good. So these definitely are not parabolas, and yet it works. It works as a waffle. So a hyperbolic paraboloid can have straight lines as an outcome, or a parabola, but if you just rotate just a tiny little bit and create an orthogonal grid, it doesn't matter what type of curve you get as an outcome, it'll work, okay? So feel free to be a little bit creative with that as well, okay? So let's do it. Let's create some planes. So we're gonna generate some points in the X direction and the Y direction. and we're going to place planes on them, okay? So if I want to generate a number of points, I would basically go grab, we're not going to draw them in Rhino now. We're actually going to use Grasshopper for its benefits. So if I were to construct a point and I put a number into that, let's say if I were to put a range, if I were to put a single number in the x direction, then we can see that point there. If I put this into a slider, set that to 100, as I run that slider up and down, my point moves, yeah? What would you suggest would be a way of producing more than one point? Array. Like we need, how many numbers need to go into the point component?
Oh, 3.
Or just more than one? Yeah, right? Yeah, it could be 4, right?
4.
You can make it 5?
Oh, really?
Well, if you made 5 points, how many numbers would you have to put into the component?
Yeah?
Okay, I'm just trying to, get some lists, get everyone back into thinking about lists. Okay, so if I were to put a range in with a set in sequence, there it is, range. If I were to grab a range, then what range does is it takes a domain. So if I would put just a normal slider in this, it's going to go from 0 to that number. It's going to divide it by a number, and it's going to produce a series of points, yeah? So this is giving us 11 points because I've got the number 10. So it's dividing that by 10, getting 11. But do you feel as if that is somehow relating with our geometry currently? No. Okay, so what we can do is we can analyze our geometry to work out exactly what the distance is from this point to this point, and this point to this point, to then give us the domain to divide between, okay? So what we're going to do is we're going to grab the bounding box component. What that will do is if you plug your geometry into it, it will produce a box that surrounds the geometry in all directions.
And should we just put in the one module? Or
The what?
when we plug in the shape, should we do the whole shape or just one module?
One module. It depends on everyone, but it shouldn't matter, okay? But it's whatever you want to waffle.
Right.
Cool. This will change. This will break a bit if you're oriented the wrong way, but we'll get to that, okay? Okay, so we have a bounding box here, and what we are going to do is we are going to produce, from that bounding box, we're going to extract the box coordinates. So with deconstruct box, that will produce for us the x domain, the y domain, and the z domain of that box. So if I now plug my x domain into range to divide it up, then you'll note that the points are now being divided between the extents of the box. Do you see the points? I'll turn the box off. Do you see how the points now line up with the whole model? Because what we've done is we're using the system to measure the paraboloid, get its extents in the x direction, divide those extents as a domain into a number, and plug them into some points as their x, yes?
I'm confused on what's one of the things doing. I think maybe I've kind of the wrong thing. I've got like a cube.
Yeah, that's perfect.
Oh, that's right?
Yep, so that's what bounding box produces.
Oh, right.
Hide the bounding box.
That one.
Yep.
Construct.
Oh, okay. And I connected it to that there.
Yep, so just show your geometry again.
Sure.
Yeah, you can see how it's moving along that in the x direction,
Oh, right, yes. Okay.
the full extent. Yep, no problem. Cool. Okay, So guys, just to explain, what we're doing is we're measuring the box. We're getting the box, we're getting its domain, because you can define a box by domains, right? In the X and Y and Z direction. And we're using the domain from that box to divide a range up to put the points in. Okay, are we good? We're there?
If I want to go this direction.
We'll deal with that later. So from this, we can produce a YZ plane. So if we're creating points in the X direction, then the plane that we're going to cut is Y and Z. Okay? So if we grab a YZ plane and we plug our points into that, that'll generate the same number of planes at those points. Cool? Yes. Pardon? Way too many.
It looks like a solid rectangular.
You're using. Sorry. This needs to be flat. There you go. That's better, right? When you. We only want one of these, so we only want this one. See? So guys, this is kind of why at the beginning I pointed some stuff out. So if you're working on more than one geometry at the moment, it's going to actually stop working. So we only want one surface or one solid, okay? So that's why I told you guys to join it. Now, a lot of you might have geometry that might look like this. You might have cables that look a bit like this, okay, where they're dotted. So what that means is you've got branches, and when you put them into join, the join's not going to join them because it sees them in separate groups. So what we just need to do is make sure your join is set to flatten as it goes in, and that way it'll make sure that everything's joining together instead of just separate things. Okay, but so that's just one little fix for I think maybe U3. Okay, so we've got our plane. If we were to do an intersection, do you remember from last week I explained there were two types of intersections? Can you remember them? Or for example, do you feel as if there might be some information anywhere in front of you if you, for example, go to the intersection ribbon, what those two different types are?
Mathematical.
Right, mathematical and physical. Anyone but Arlene. If we've got a plane and a solid, what type of intersection do you think that is? Do you think it's mathematical or do you think it's physical? Just if you recall the difference between the mathematical intersections and the physical ones, if I've got my two arms crossing each other, are they intersecting? Like, let's say they can intersect. Are they intersecting? Yes. Okay, but do my arms go for infinity? No. So if I were to separate my arms, do they intersect? But if my arms were now infinite, would they be intersecting?
Yes.
Okay, so that intersection would be considered mathematical, and this intersection would be considered physical. Okay? So if we've got something here, like a plane, that is infinite, what type of intersection do you think it would be? Perfect. So if you go look in mathematical, you will probably be able to find a component that finds the intersection between planes and B-reps. Correct. So if I grab my solid and I plug that into the BREP part of the plane intersection, and I get my planes and I plug them in, if I hide everything but the outcome of that, what that will do is produce the sections that cut through those planes. Cool? So, can anyone observe something that might not be achievable in reality? If I were to just straight away start cutting these in the laser cutter, let's say we're not worrying about the waffle, can anyone see anything that's not achievable in reality? Huh? No, they're not. They're definitely not twisted.
Oh, I don't know why they're not.
No, they're on the plane. They're definitely. They're not laser cuttable. Yeah. Okay. Forget that part. Yep. Yes. Give me. Is this a question?
This
No. We're working on this one, man.
but oh,
You need to plug these points into there, or otherwise it won't know where to put the plane.
Do you know
Yeah.
why one of them like,
Yes. This is where. This is
Oh,
where.
that's okay.
This is where the answer comes. Yes.
I don't know why.
You don't know why.
Yeah,
Is that you don't know why it doesn't work?
yeah,
Well, you've got 4 points.
yeah.
Surface. Where is it? Is there a 4-point surface? No. Because how many points have you got? You've only picked 1 point. How come you're not using the surface that you did last week?
In the last week.
Yeah, you should be working on the surface that you did last week. Yeah, but I think you're going to have the same issue as this guy, man. Where's your surface? You don't have a surface. You need to be working, guys. Yeah, you need to be working on the surface from last week. Okay. So see the surface that I've got here. I'm obviously not a student in this class. I'm a tutor, so I'm not doing the assignment. Yeah. Yeah. So I've just quickly created a proxy of the surface that you would have had from last week. Yeah. So that's this surface here. So don't follow along at this point. This point is proxy for what you did last week. Yeah? Yeah? So go grab the surface that you produced last week, and we're going to use that instead of the 4 points. Those 4 points are just for me. Okay? No, you don't understand? Good. Pardon? Does that make sense? Really? You've got a bunch of these surfaces, right?
Yeah.
So let's just work on this one, okay?
Okay.
So let's hide these, yeah?
Okay, I know.
Now,
Now I know.
let's go,
From this, yeah.
does that make sense now?
Yeah.
Cool. Can you explain it to these guys? Thank you. Yeah, mate.
Sorry. So
Yours isn't solid. So what's the thickness of that extrusion?
I haven't said it.
Can you put a slider into that?
Into the Z unit?
Yep.
Oh, okay.
And that might give it a bit more thickness. Cool? Cool. Yes.
We use this one from last week.
Yeah, we need to use this.
Okay.
But you should be working maybe with just one segment.
Okay.
Mind you guys, if you've decided to do a different, like if you're Candela, you should be working on your Candela job, yeah? Okay.
On my shape is quite strange that it's triangle inside and the hyperbola outside.
Okay.
And here.
Ah.
I don't know why.
Okay, just come back. It's because you've got a whole bunch of. It's this point here.
Oh, I forgot.
We just need to flatten that.
It's still.
What's going on here? But you've got what's going on? May I just quickly?
Sure.
Good job in terms of, like, it's definitely, how do I select all?
Select all? Okay.
What? It's Control A. Oh no, because it's a Mac, so usually you have to use Command.
Oh, because it's Windows.
I'm surprised this even has Control. So it looks like there's some. This is from your actual scripting, right?
Yes.
That's what's been produced. Can we just work on
The outside.
just one part?
Sure.
So
Definitely sure.
what's going on here? So that.
I think the thickness,
Hang on. What's this? Is this something you made?
Yes.
Okay, so it's just this particular script is creating also the triangles.
Because I need.
Okay. Let's just use this. Yeah. Done. So, but let's just take this one, and we're just going to do it to 1, okay? So that'll thicken it up. See how it gives it thickness? And then this is cutting a section through it, like. Can you just move your head a bit?
Oh, sorry.
Thank you. See, this needs to be X, not P. And see, we're getting these. What's going on here? Shit. So these aren't all joining, and I think it is because we just need to get rid of. What's that? I have no idea what that is. That's your computer doing that. That's so much better. And does this work better? Oh yeah, it looks so much better. So we should be getting. Why are we not getting curves through it? You're not cutting through it. This needs to. That's the B-rep you're cutting through, and these are the planes. Yeah. See that now. See how it's cutting through? Yeah? Okay. See those sections now? Yeah, okay. So, and as you change the thickness, it gets thinner. Yeah? No problem. Okay.
Do you know why it might become like this? Like, it doesn't follow the curve.
You mean the surface?
Yeah.
It is following the surface. That is the surface at that point. Yeah, that's it. Huh? It didn't work.
I'll just unhide these.
May I?
Yeah, sure. Sorry.
Because like it's already like that. I screenshot that and I just make it properly.
Even when I increase the amount.
I did my script on one page, but you can't even read it. Yeah, I couldn't fit it,
Can we set that to 100?
so I did my script. They're so cute. Good. They're so small. Oh, that's so cool.
Yeah, what is going on?
How'd you make it look like that? I just rendered it. Oh. But she's like, we'll be evaluating.
I've extracted it from the list.
And I'm like,
There's a trim surface.
but like it shows.
How come we can't extrude it?
Did I extract it properly?
Yeah, it's fine.
Yeah. It'd be so hard to like do the waffle.
Strange. Really strange. Can we just do, okay, let's just do this then. Let's just work on this one for now, and then I'll help you out later. Yeah, that's working. It's definitely working, that one. Can we you just work with this one for now, okay?
We create a waffle one.
Yeah, we'll just create a waffle and I'll help you out, okay? Because it looks like you've got maybe an invalid surface somewhere. Cool, but you see that working now?
Yeah.
Okay, back to actually teaching. Okay. Yeah? Well, that's because you're cutting. Why do you think it's not cutting, giving you the solid? Are you cutting the solid or are you cutting a surface? What are you inputting into the B-rep and plane intersection? What is going in? So if you were to say make a cake, put mud in and put eggs, would you get a tasty cake? Mud and eggs? No? Or sand? Like you put sand in and eggs. Mix them up? So you're telling that component the wrong thing. So when you're cutting through a solid, are you cutting the solid or are you cutting the surface?
Solid.
But are you cutting the solid or are you cutting the surface? So what do you want to be cutting?
Solid.
So what do you think you should be plugging into that component?
Actually, this surface is the solid.
Okay, is this a solid or a surface? No, it's not. It's a surface. And when you extrude it, is it a solid or a surface?
Extrude is solid.
Okay, so what do you want to be cutting?
Solid.
So what are you cutting currently? Look at the component that's going into the cut, the B-rep cut. Yeah, what is going into that right now?
It's just
No, what's going in, not what's coming out. What is going in? What's going in?
I should connect this.
Yeah. Yes.
I just draw the line.
It's just drawing a line. It's not drawing these. Okay. What are you cutting? Are you cutting a solid or are you cutting a surface? Are you sure you're cutting a solid? Look at what you've done. Look at what you've done. Look at what you've done. Are you cutting the solid or are you cutting the surface?
Just a solid.
Are you sure about that? If it's only producing the lines, is it produce? Look, Are you cutting the surface or are you cutting a solid? Surface, solid. Surface, solid. Which one of those is going into that?
Oh, it should be a solid.
Yes.
Oh,
See how that's now producing the outcome that you want?
yeah.
Yeah? Guys, I'm not going to be around forever. Okay? You're going to need to look at what you've inputted and look at what is being output. You can't just follow these scripts along blindly, okay? If you just follow them along step by step without understanding them, then there's no point. Okay? Except for what I did in that 10-minute exercise last week. Okay? Cool?
You can plug your laptop in now.
Thanks. Have you found a PowerPoint?
No, I'm just going to copy off Curtis. Follow along.
Copy off Curtis.
I'm going to follow
I'd pick someone other than Curtis to copy off. I'm just teasing Curtis. No, it's because his surface is invalid. That's why. But yeah, cool. Thank you. Is that why why did you decide that? Because my power's going low?
save it. I don't want to watch. I can watch the video later.
Did anyone get electrocuted when they plugged this in?
No.
Okay, good. The cable's torn. Good. I'm glad. Like, well, I couldn't, well, yeah. Okay, back to this. And that got recorded as well. OH&S issue. Oh, look, I've just unplugged the laptop. Okay, it's all safe now. The electrical thing's all been covered up. Excellent. Okay, done, fixed. So, what thing do you see currently that is not capable of being made in reality?
Little lines at the ends.
Yeah, the little lines at the ends. They're like, are they closed lines or are they just lines? Okay, and why do we think they're being produced?
Because it's the end point.
Why do we think they're being produced? You can't give me that type of face, like, don't ask me. Why do we think they're being produced?
As we have a plane on this, because we extrude, so we have.
We're cutting a plane through the very end of a surface, right? If we were to cut a plane across the top of a sphere, like the very top, what do you think the outcome would be? A point, right? And a point's not laser cuttable, yeah? So there's a few ways we can get around this, and the easiest way is that we just ignore the ends, yeah? So what we're going to do is we're going to use cull index to remove the ends. We've done this in the past, I believe. So we'll just grab a cull index and we'll plug that in. And the indexes that we want to cull are the start and end, which I'm going to sound like a broken record now, is 0 and -1. I feel like that should be ingrained in everyone right now. Is it? Excellent. So that'll get rid of your weird curves that you'll probably all have. You're guaranteed to all have them, unless someone's made a cube. Okay, so all we've done is we've removed the first and last range number, which means that we're not producing a plane at where x is minimum and maximum. Okay? Need a drink. Okay, next step. Just to avoid having to copy and paste a few times later, we are going to turn this into a boundary surface. I think this is the first time I've ever shown you boundary surface. Okay, we've extruded, we've lofted. We can produce surfaces by just putting boundaries, giving a boundary, like a closed outline. As long as it's planar, it'll produce a surface. Okay, I think I did show you this when we made the 6-sided surface, right? How I showed you a polygon, and to prove that it was 4-sided, I had to make a surface like this to make a polygon, yeah? So if I plug our closed curves in there, it's going to make a whole bunch of planar surfaces. The really cool thing with this is if in the future you do somehow manage to produce a surface that is a curve that is not planar, then at least these components won't work. When oh shit! Oh no. Okay, another thing, guys. If you save your script early on, then it gets auto-saved.
Oh, it's just missing my color.
Yeah. Okay. So, we need the other direction. What's the other direction? Z. So the plane, what direction of the plane, what orientation is the planes currently? They're YZ, yeah? And they're placed in the X direction. So we need to work in the Y, we need points along the Y direction, and the planes that we're going to put there are what planes? If we're using YZ planes currently, XZ or ZX plane. Excellent. Okay, so what we're going to do is we're going to copy this set of components. I'm not holding shift, that's why it's not working. We're going to copy these guys. We're going to plug Y into range, but now instead of controlling the X direction for the points, so we don't want the points to be doing this. These points now need to be going in the Y, so we're going to slip the X into the Y. And instead of generating a YZ plane, we need to be generating an XZ plane. And doing so will produce the surfaces in the other direction. How's Romeo going? You understanding this all, Romeo? What I don't understand about Romeo is he seems like a young dog. How old is he? Okay, he is an adolescent to adult, and yet all I've ever seen him doing is like chill out so much. Like he's. What drug have you given him? Okay, so he's been trained to literally do this.
Yeah, pretty much.
Okay, that makes sense. Okay, because I'm like, how do you make a dog act like that? Yeah, that sounds like she's definitely drugging him before he comes in. Romeo. Oh yeah, yeah. Romeo. Oh Romeo, wherefore art thou Romeo? Sorry, I know. Yeah. Go to the restroom. Why? What time is it? 3 o'clock? Yeah, it's only 11:28. We've got plenty of time. Plenty. Yes.
I still think it's not.
You still think it's not working? Corky. It's working.
Like the line goes like in and out.
What is that?
So it's not working, right?
Okay, yeah, but we'll deal with that later, okay?
It's great.
Because it is
Maybe it's this.
the error there. It just says the intersection failed. Don't worry about that for now, okay? Just don't worry about it. Oh shit. So you guys plugged it in, but then you didn't plug it in my computer. Okay.
这个挺大概才忘了。
因为抖妹你在那个点上还是错的，对吧？我跟你说不影响的，只要是这个 box 里面横竖是垂直的就行。
Okay. So we have, guys, Guys, we gotta get through this, okay? Billy's making me worry. I'm running out of time. Okay, so we have 2 sets of curves, and we need to start creating slots. Right, so if we were to move this onto the ground plane now and start laser cutting, they're going to collide, yeah? So we need to start getting these slots to work, okay? So we need to generate something that tells us where the slots go. Now there's 2 ways of doing this. I believe the other class is going to do this by finding a physical intersection. So they're going to take the 2 surfaces and find where the surfaces intersect. If I were to take 2 surfaces and find their intersection, what do you think their outcome would be?
Lines.
Curves.
Oh, curves.
Curves, yeah? Right. If I were to take the planes from the opposite direction and find the intersection with our curves, what do you think the outcome would be? A good answer would be the same. It'd be the same, right? Because these are planar, and therefore if I were to take the planes that define them and did an intersection, I'd get the same result. Now this is really important, not for this particular assignment, but for using this script on any geometry, okay? If I were to create a shape like this and cut through it, how many curves would my plane produce? Let me draw that again. Actually, let me do one of my favorite foods of all time. If I were to cut through a donut, huh? A very what? A very what? If I were to, it's 3D. If I were to cut through a donut, like so, how many curves would it produce? Are you sure about that? 2. It would produce this circle and this circle, yeah? Because it's cutting all the way through. 1, 2, yeah? So the issue is, if you want to find where maybe this, when the work that we're doing currently, we're going to be dealing with trees now, and the trees need to be implemented because there is the potential of producing 2 curves from one plane, okay? So when we cut our BREP and plane, you'll notice that the list that we get as an outcome it doesn't look like a standard list anymore. What is in that list that looks a little bit different? It's got all these numbers, right? So this is something that was mentioned in the lecture. These are branches. Who actually followed along the lecture? Some of it? Okay. Okay, so there's 2 important things about branches in Grasshopper. The first is what they are, okay? We can think of any list in Grasshopper as a tree. That's what Grasshopper calls it. So this particular list is a tree. If I had a list of these 3 students, I've forgotten your name. Teresa. So if I've got Blair, Jonathan?
Yeah.
Is that like that? John's fun?
Yeah.
And Teresa? This is a list, 0, 1, 2. If I were to represent that as a tree, I could just consider that as one trunk of a tree, okay? So this is a tree. I think it'll make a bit more sense soon. Okay, so what Grasshopper does is it says you can have a list of items such as Blair, Jonathan, and Teresa, yeah? But I could have a second list, I'm not even going to bother, but these guys' names, right? So I've got a bunch of 3 students, and I've got a group of 5, yeah? These are 2 separate lists, but I could actually have them in the same tree, okay? So if I were to, I could actually represent this class as a tree of lists grouped by each row of tables. So this guy here would be in a list by himself, just one item, yeah? And so would Sarah, but maybe we could throw Romeo in there as well, yeah? Cool? So if I were to say, okay, this group here, 1, 2, 3, 4, 5, that's a list of 5, we can write that as a single list, yeah? So each separate list within a list, so you can have a list of lists, and that's what's happening here. We've got 9 lists inside one list, and each list only has one item in it, yeah? If we were to cut a section through a donut, like so, that would result, the first plane would produce how many curves? So in my lists, how many lists do you think we will produce? 3 lists, right? So this is going to produce list 1, this is 0, this is going to produce list 1, and this is going to produce list 2. So list 0 is going to have how many curves? Curve. And then list 1 is going to have how many curves? Right. And then list 2 will have how many curves? Does that make sense? You too. Does it make sense? Does it make sense? Okay. So, what this is doing is it's automatically assuming that you could produce more than one outcome. And it is then producing these branches that then group them, okay? So most of you do not have geometry that will do this, but you need to understand this, that it can produce it, okay? And that's why it's doing it. Another component, has anyone played around with offset? Yeah? Another component that does this is offset. So if I have this shape and I offset in one direction, how many curves does it produce? The green's terrible. How many curves does it produce? 1, right? But if I were to offset in, it produces 2, right? So if you're doing this to multiple curves, and there's the potential that it can produce more than one outcome, then Grasshopper will automatically put them into branches so that you know which curves belong to which object. So object 0 will produce a branch addressed at 0. We'll get into this more. These are the types of things that I was talking about where you were saying, oh, could we just not plug these all into the one component? Understanding how trees work and how to manipulate them and use them is really how to use Grasshopper at an advanced level, okay? So at the moment, we're just going to use Grasshopper and branches at a 2-dimensional level, okay? As in, we should only really be seeing one number in this branch, okay? What do you see here? There's like 1, 2, 3, 4, 5. There's 5, right? But if we run that all the way down, the only number that actually changes all the way along here is the very last one. So there's a function in Grasshopper that can help us see this a bit simpler, and that's simplify. So if we run any list through a simplified tree, what it will do is it'll just get rid of any unnecessary 0 from that list. And so here now we can see 0, 1, 2, 3, 4, 5. It's nice and clean, okay? Cool. So we can also understand this data not only as a tree. You know how I kind of like to warp things? So like I took lists, like a list that looks like this, and I made it look like this. Yeah? So as we get to the end of the list, if we take another step, we go back to the beginning. Yeah? So lists or trees can also be understood like matrices, okay? So for every for every number that we've got as a branch, we have a column up here, 1, 2, 3, 4, 5, yeah? And for every item that we have in the list,
跟你说不影响的，只要是这个 box 里面的横竖是垂直的就行。
okay. So we have, guys, we're gonna get through this, okay? Billy's making me worry, I'm running out of time. Okay, so we have 2 sets of curves, and we need to start creating slots. Like, right, so if we were to move this onto the ground plane now and start laser cutting, they're gonna collide, yeah? So we need to get started in these slots to work, okay? So we need to generate something that tells us where the slots go. Now there's 2 ways of doing this. I believe the other class is going to do this by finding a physical intersection. So they're going to take the 2 surfaces and find where the surfaces intersect. If I were to take 2 surfaces and find their intersection, what do you think their outcome would be?
Lines.
Curves.
Oh, curves.
Curves, yeah? Right. If I were to take the planes from the opposite direction and find the intersection with our curves, what do you think the outcome would be? You can, a good answer would be the same. It'd be the same, right? Because these are planar, and therefore if I were to take the planes that define them and did an intersection, I'd get the same result. Now this is really important, not for this particular assignment, but for using this script on any geometry, okay? If I were to create a shape like this and cut through it, how many curves would my plane produce? Let me draw that again. Actually, let me do one of my favorite foods of all time. If I were to cut through a donut, huh? A very what? A very what? If I were to, it's 3D. If I were to cut through a donut, like so, how many curves would it produce? Are you sure about that? 2. It would produce this circle and this circle, yeah? Because it's cutting all the way through. 1, 2, yeah? So the issue is, if you want to find where maybe this, like, when the work that we're doing currently, we're going to be dealing with trees now, and the trees need to be implemented because there is the potential of producing 2 curves from one plane, okay? So when we cut our BREP and plane, you'll notice that the list that we get as an outcome it doesn't look like a standard list anymore. What is in that list that looks a little bit different? It's got all these numbers, right? So this is something that was mentioned in the lecture. These are branches. Who actually followed along the lecture? Some of it? Okay. Okay, so there's two important things about branches in Grasshopper. The first is what they are, okay? We can think of any list in Grasshopper as a tree. That's what Grasshopper calls it. So this particular list is a tree. If I had a list of these three students, I've forgotten your name. Teresa. So if I've got Blair, Jonathan?
Yeah.
Is that like that? John's fun?
Yeah.
And Teresa? This is a list, 0, 1, 2. If I were to represent that as a tree, I could just consider that as one trunk of a tree, okay? So this is a tree. I think it'll make a bit more sense soon. Okay, so what Grasshopper does is it says you can have a list of items, such as Blair, Jonathan, and Teresa, yeah? But I could have a second list, I'm not going to bother, but these guys' names, right? So I've got a bunch of 3 students, and I've got a group of 5, yeah? These are 2 separate lists. But I could actually have them in the same tree, okay? So if I were to, I could actually represent this class as a tree of lists grouped by each row of tables. So this guy here would be in a list by himself, just one item, yeah? And so would Sarah, but maybe we could throw Romeo in there as well, yeah? Cool? So if I were to say, okay, this group here, 1, 2, 3, 4, 5, that's a list of 5, we can write that as a single list, yeah? So each separate list within a list, so you can have a list of lists, and that's what's happening here. We've got 9 lists inside one list, and each list only has one item in it, yeah? If we were to cut a section through a donut, like so, that would result, the first plane would produce how many curves? So in my lists, how many lists do you think we will produce? 3 lists, right? So this is going to produce list 1, this is 0, this is going to produce list 1, and this is going to produce list 2. So list 0 is going to have how many curves?
1.
Curve. And then list 1 is going to have how many curves?
2.
Right. And then list 2 will have how many curves?
1.
Does that make sense? You too. Does it make sense? Does it make sense? Okay. So, what this is doing is it's automatically assuming that you could produce more than one outcome. And it is then producing these branches that then group them, okay? So most of you do not have geometry that will do this, but you need to understand this, that it can produce it, okay? And that's why it's doing it. Another component, has anyone played around with offset? Yeah? Another component that does this is offset. So if I have this shape, and I offset in one direction, how many curves does it produce? The green's terrible. How many curves does it produce? 1, right? But if I were to offset in, it produces 2, right? So if you're doing this to multiple curves, and there's the potential that it can produce more than one outcome, then Grasshopper will automatically put them into branches so that you know which curves belong to which object. So object 0 will produce a branch addressed at 0. We'll get into this more. These are the types of things that I was talking about where you were saying, oh, could we just not plug these all into the one component? Understanding how trees work and how to manipulate them and use them is really how to use Grasshopper at an advanced level. Okay? So at the moment, we're just going to use Grasshopper and branches at a two-dimensional level. Okay? As in, we should only really be seeing one number in this branch. Okay? What do you see here? There's like 1, 2, 3, 4, 5. There's 5, right? But if we run that all the way down, the only number that actually changes all the way along here is the very last one. So there's a function in Grasshopper that can help us see this a bit simpler, and that's simplify. So if we run any list through a simplify tree, what it will do is it'll just get rid of any unnecessary 0 from that list. And so here now we can see 0, 1, 2, 3, 4, 5. It's nice and clean. Okay? Cool? So we can also understand this data not only as a tree. You know how I kind of like to warp things? So like I took lists, like a list that looks like this, and I made it look like this. Yeah? So as we get to the end of the list, if we take another step, we go back to the beginning. Yeah? So lists or trees can also be understood like matrices. Okay? So for every for every number that we've got as a branch, we have a column up here. 1, 2, 3, 4, 5. Yep. And for every item that we have in the list, we have another index, 0, 1. So for example, if we go back to the donut, the first curve produced goes into branch 0, and it goes item 0. So there's a curve, yeah? And then the second intersection will produce 2 curves, so that's branch 1, and that will produce curve 0 and curve 1, and then branch 2 goes to 2, and we get 1. Does that make sense? So we just have to start thinking about data in really abstract ways, okay? Back to this. It's going to be really important that we actually keep this in a branch format now. In the past, I told you guys flatten, yeah? So what flattening does is it basically takes each of these branches and it puts them 0, 1, 2, 3. It literally just takes them consecutively and stacks them on top of each other. Okay? That's what flattening does. It destroys the branches. It just makes it a single trunk. Hence why flattening gives us a stump icon. Okay? And it's you need to understand it to know why it's a stump. Okay? So what we don't want to do is we don't want to flatten it, because if we want to move this geometry from its 3D coordinate to the flat plane, there is a corresponding plane for each element. Yeah? So that corresponding plane is we can see there are I'm just going to reduce this number to 3 for now, just to make it simpler to understand. Let's make it 4. So we can see there are 4 branches after they get simplified. There are 4 branches, And how many planes are there? Sorry, did I say 4 branches? There are 3 branches. And how many planes are there? 3, right? So which plane do you think belongs to each branch?
The zero, the zero accordingly.
Yeah, so it's in order, right? It's in consecutive order, yeah? So the beautiful thing about this, though, is that we will eventually need to get it, the beautiful thing about this is it keeps it in order, but the problem is for this to relate to this currently, if we were to try and run these through as a function right now, Grasshopper looks at the first branch when it runs a function, and then it looks at the first branch and it tries to find all the elements in that to work with. So if we run this and this together, do you think this particular item will be affected once or 3 times? 3, it'll be affected 3 times. So for this, we only want this plane here to affect this surface. So to do that, we need to turn this into a similar tree structure to this, okay? And fortunately, we know that for every plane there needs to be a branch. So the function that does that is graft, okay? So all graft does, just like the way trees actually work, if you want to produce a new branch, you must graft it. So grafting a tree will produce a single new branch for every item in each list, each and every list, okay? So now we have a branch and a branch that function together. So what we're going to do first is I'm going to just transform them and put them on the ground so that they're laser cuttable, and then we'll work out where the slots are, okay? So we've now got a branch for our plane, and we've got a branch for our surface. So we can now take our surface and orient it from that plane to the flat plane. So like so. And if we want to make our plane, like we want to move our planes, so let's get a seat. So right now, what that's doing is it's moving these 3 surfaces. I'll just hide everything. What it's doing is it's moving these three surfaces from their corresponding planes to the XY plane. And so that's why some of them are overlapping right now, because when we look at it at that plane, they overlap, yeah? So what we can do is we can produce a number of points, just like we are constructing here. So if we go grab a construct point component and we count the number of planes that we're using, so in this case we've got an XY plane, so we're going to count the number. We'll plug that into a series, and the number of points that we're generating is the C value in a series, so that's there. And we want a slider to determine the distance or the step. We'll plug that into Y, and that will then plug into the XY plane. And an important thing is our XY plane now, it looks very similar to how it looked previously before we grafted, right? So what we need to do is also graft that so that each branch only applies to each branch. So what that now gives us is a slider to then spread our particular elements out. Cool? Okay, back just to repeat. So what we need to do is we need to count the number of planes that we're sectioning with. So we do that by using this list length. So if we plug that into our XY plane or our XZ plane into list length, that will tell us how many planes there are. So this tells me that there's 3. Okay? We're then using a component called series. Series takes a start number of 0, so we're going to use 0 as a default, a step number, so in this case 6, and a count. So count is 3 because that's how many we've counted. So what it will do is it'll produce a number from 0, it'll step up by 6 3 times. So it goes from 0, 6, 12. If I set this to 5, it'll go 0, 5, 10, right? And we're plugging that into a new construct point component. So you can see here I'm constructing these 3 points. We're placing 3 XY planes on them because XY is the plane that we can laser cut, yeah? And we are orienting our boundary surface, and that then allows the components to spread apart and not be stacked on top of each other. This might, like, this needs to be done by everyone. It's either doing that or doing it manually, right? Like baking and then having to move them all manually. But this is important, yeah?
Mine's not showing anything.
Have you grafted it?
Yes. It's not showing anything on
Yeah, that's fine. There's a price tag. Yeah, they are there. They just see. Okay, so another thing, guys, if you've modeled it away, it's going to go back to like 0. It's going to go back to the origin point. Has this made sense? Yeah. You get some cheeky smiles like, no, but it's working. Is it working?
Mine's going left.
Huh?
Mine's do that one.
Yeah, just.
That's just moving.
You're plugging it to the start, not the step.
My bad. So I should plug in.
Yes.
This one, can number be anything?
Yeah, it can be anything. So as you move that up and down, does it move the pieces apart?
Yeah, it does.
Yeah. Yes. Don't worry too much about that. That's fine. It's still working. Cool. Okay.
Okay, we need the simplified icon here. Like, I'm not sure.
No. The only reason I did that was to show you the branch. So it's just all that's doing is making sure. See this branch here? It's only 0, 1, 2. If I turn off the simplify, all it does is it's got all these like excess zeros. We don't actually need them. So what it does is it just gets rid of any excess element that you don't need. Okay? Cool. Okay, so we can cut something in 3D space and we can orient those cuts into the cutting plane of a laser cutter. Excellent, right? Now the only problem is now if we were to apply this to the other side, which we can do. So for example, we can copy all of these elements and we can paste them and use them above. So we're getting the length of the plane, the list of planes. We're getting our boundary surface, which is being oriented, and we just need to take our planes and graph them. And we can even, what we could probably do as well is we can put a slider into the X component of one of our point lists, so we can then like keep them separate. Yeah. Like basically the same rules applied to the 2 lists. You just have to use different inputs. We're just using a different set of planes. Yeah. Yep. So what we just as a thing, I've made a slider to put into this construct point, so that way I can control the X location of this list. We are going to copy the orient, the graph tree, and these like series of components that produce the points that we were going to orient to. So we're going to copy them, and we just basically the most important thing really is this plane. So this plane here is going to plug into the graph and the list length, and then our boundary surface is the thing that's getting reoriented, and we can change the slider on that initial on this construct point, so that way it's the same. Not the same. It doesn't clash. Cool. So I guess the most important thing is the plane needs to basically plug into this graphed tree and the list length, and our boundary surface is the thing that's getting oriented. So that's really the only two different instructions. So we could make a cluster for this, but we're not. Yeah, just different inputs. Yeah, same process, different inputs. Cool. Okay. Now, technically, if I laser cut this, we'll get a whole bunch of shapes that we actually need. But what's the problem? It's going to clash. The timbers are going to clash. We're going to create slots. Okay. So this is where these two lists they kind of start interacting. Okay. Because I've got a series of boundary surfaces here. I'll just isolate them. So I've got a series of boundary surfaces in one plane. Yeah. And I've got a series of planes that go in the other direction. Okay. So I want to show you how to do this, but I also want you to understand what it's doing. When I have a list of points in Grasshopper, so I've got two lists here, list A and list B. When I have more than one point, when one list is longer than the other, what happens is, if I were to draw two lines, a line between them, or run any function between them whatsoever, it will take item 0 from each list and connect them. It'll take item 1 and connect them. And then when it gets to item 2, yeah, it goes back to B1, right? Okay. That same rule applies with trees and branches. Okay? So, if I have a branch called 0, 0, another branch called 0, 1, and these two branches are considered A, okay? And I've got a branch, another list called B, and that's 0, 0, right? So if I were to just create a list here of 0, 0, 0, 1, and 0, 0, A and B, and in here I've got 2 points, 2 points. So what it does is it steps over in the same system, but it does it on a higher level. So what do we do first? We look at item 0 and item 0. So what does Grasshopper do? One level up, it looks at the first branch, and then it looks at the first branch, and it then goes item 0 goes to item 0. So therefore it will produce that line, and that line, or these two. Okay? Then it goes, I've run out of branches in B. So if we ran out of items in B, what would happen? It gets the last one to the last one, right? So therefore, this branch is going to apply to which branch in list B? The only branch that's there, right? So therefore, item 0 goes to item 0, and item 1 goes to item 1. So it would produce that outcome, right? It's really simple, like it's base level, right? So this is where things get really interesting with cross-referencing. if I have a list of 9 surfaces, and a list of planes, and I want those planes to apply to every surface, like I want to find their intersection with everyone, what I can do is I can cheat or game the system that works like this, whereby we can say every surface is in a branch, is in their own separate branch. And so, for example, we have 2 branches. And if we have every plane in a single branch, plane, then what will happen is this surface will get applied to these 3, and then this surface will get applied to these 3, and so on and so forth. So we're effectively cross-referencing the geometry with every other geometry. Okay? Cool. So, what we can do then, fortunately, these planes are in a single branch. They're not grafted. We have them here in one branch. And we also have all of our boundary surfaces in branches. Okay? So we already have the data structured in a way that will work for us. So all we need to do to get the intersection between the two is go and grab another B-rep and plane intersection, where our B-reps are our boundary surfaces, and our plane is the opposite plane, the plane that goes the opposite direction to those surfaces. So if I plug that in now, you'll note that we can see all the lines that those planes cut through the surfaces. Cool. So I'll hide the surface geometry because it might be a bit hard to see. Can you see the lines that we've produced? I'll make the thing thicker as well. Can we see those lines? So a lot of you might notice that this intersection component turns red, right? Normally, that means something bad has happened. Yeah? When you get these little errors, it'll always give you this little pop-up button that you can click, and it will tell you intersection failed. What that's actually telling us is that this plane here isn't intersecting with this geometry. Yeah? Because there's nothing there to intersect, so therefore the intersection failed. But guess what? We don't care. Okay? It doesn't matter. So even though it's turned red, it doesn't matter. So sometimes red things in grasshoppers are okay. So we've got a center line for our lines, for our slots, right? But there's a few things that we need to do to it. If I've got a line that goes all the way through. So before we do anything now, sorry, I just can't see anything here. That's fine. Sorry. What we need to do now is we need to give these thickness, because what type of material are we using? Plywood. And plywood has a thickness, right? So we need to produce a slot for the plywood to go through with thickness. Now, I really like the functions that we're gonna step through. It's really easy to do these functions in 2D. It's really challenging to do them in 3D in this space. So what we're going to do is we're going to move all of these lines, these center lines, to the plane that we're using to laser cut. Because all the functions that we have to do on them from then on are just 2D. Okay? So there's one issue though. Remember how this intersection component works? It assumes that if it might be able to produce more than one object, right? If I intersect it with a donut, I could potentially get two outcomes for the one plane. So we're starting to see, after I simplify the branch, how many numbers are in the branch now? 2 numbers, not 1, right? Which means we're actually starting to make a 3-dimensional matrix now instead of a 2-dimensional matrix. Yeah? So what we need is, if we were to now try and move these, so we can actually use orient, right? If we want to move these lines the same way we move the surfaces, yeah? Because that way they'll end up in the exact same spot they need to be. But they're in the wrong data structure. They've got one too many branches because the system thinks, I can produce more than one curve from this. I'm going to put it in the new branch system. So this is where trim tree comes into play. And that is all trim tree does. For example, all trim tree does is it gets rid of the highest level branch. Okay? So trim tree, I really don't expect you guys to completely understand this stuff. I honestly didn't understand it for a very long time. The fact that you're hearing it a month and a half into learning Grasshopper is crazy. Like, for me, in my time spectrum of learning Grasshopper, I only understood this stuff a year in. Okay? So it took me 12 months to just work this out. So in no way does this need to be absolutely understood, okay? But purely it gets rid of the top level branch. So you can see how these are 0, 0, 0, then 1, 1, 1, and 2, 2. I know it's hard to see, but you can see them. What it does is it gets rid of that. So anything in 0 gets rid of these 0, 1, 2. So anything in 0 gets clumped together into a branch. Okay, so what we'll do is we'll just grab that so you can actually see the outcome. It's probably easier to tell based on the outcome other than just me explaining it. So if we grab a trim tree, you'll get that under set. Crashed again. If we grab a trim tree, what we'll see is the branches get pushed back into their same structures again, okay? Into the structure of just one number, 0, 1, 2, 3, 4. There are some exercises that you guys can do that will help you understand it a bit more. Those exercises kind of involve just a bunch of points. But right now, we just need a trim tree. And what that will mean is when we use our orient, the same orient with that same data structure, plugging our trim tree in. Now, if I preview the output of the orient, we can see the lines that are being moved as well. So they're there. Okay. What I might do is I'll just amp this up now. I'll amp this back up to like 10, so that we can see those lines. Cool. So there are those lines, and those are the center of the slot. Yeah? So what do you think we need to do to those lines to now turn them into slots? Divide them? Yep, that's one thing that we do need to do. So guys, if I were to take my object like this, and I were to produce a slot like that, what would happen to our object? It would just fall into pieces, right? So first thing we need to do is take our center line, and I'm using center line as a really important word right now. We need to take our center line and only get half of it. And then, what's the next step after doing that? We need to give it thickness. So we need to offset. So we'll offset at the width of the material, close the offset off, and that will leave us with a slot. Okay? Does that make sense? Excellent. So, if I've got a line and I want to split it into only 50%, get 50% of it, what are some of the techniques that I can use that I've already taught you guys? So I've got a line. If I've got a line like this, and I want to only have 50% of it, what could I do to this to just get 50%? Oh yeah, so we could do a subdomain curve. Is there another way? Evaluate will give us the midpoint, but it won't give us a segment, right? What did we use? No, divide will also only give us points. We want line segments. Shatter, right? So if we were to shatter this at 50% at 0.5, that'll give us half on one side and half on the other. Okay? So what we're going to do is we're going to grab... Now, but by the way, guys, this applies to both sides, but the other side would be the opposite. So anything that we're going to do on this side, we're eventually going to do, again, it's going to involve copying and pasting, so a little bit of stitching. But this is the same process for both sides, okay? So we're going to take our oriented lines, like so. So we can see them in green. I'll actually hide the outline. We want to shatter these lines. And which coordinate do we want to shatter at? What parameter do we want to shatter at? Yes, but now, what's required of this line to guarantee that 0.5 means the midpoint? We need to make sure that it's reparameterized. Okay? Yeah, because reparameterize will guarantee that the start is always 0 and the end is always 1. There's a chance that these lines might not be 0 to 1. They might be 100 to 105. Who knows? Okay? So that will now shatter them. Now in this case, we want let's say we'll want the ones on the bottom. So we can use a list item to pick out the bottom line, like so. And if I hide these, we can see now that it's picked out the bottom line. We've run into an issue. We'll deal with that soon. Who can tell what the issue is?
For some, it's spaced out the bottom of the.
Yeah, there's one that has them at the top whilst the others are on the bottom. So that's because the line that's generated by the section, the BREP section tool, it doesn't guarantee a certain direction, right? So just to make sure, we're going to have to do this funky little process here with the BREP plane. We need to insert into that an evaluate length or an evaluate curve. We'll use evaluate curve. So we need to plug our curves into that. We need to set the parameters of that to 0 and 1. And that needs to be a multi-line. Plugging that into the T, that'll give us the start and end points of all our curves, like so. We need to deconstruct them to get the Z coordinate of the point. So that'll give us, the one is 15.8 and the other is 12.8. We then need to sort the list out of that Z, and we need to also sort the points synchronously. This is just a fix we're running out of time, so I'm just showing you a fix to solve this problem. And then we need to produce a polyline from the A output of that. And with that polyline, we are guaranteeing that every line is going vertically from bottom to the top, because we've sorted the points by their Z values. Okay? And then we can now use this polyline to plug into the trim tree. And what you'll notice now is all of our slot positions are all on the bottom now. Okay? So that's going to solve that problem. Cool? Then we're going to take our center line and we want to offset it. Okay? What distance do we want to offset it? The thickness of the material. Okay, so I'm gonna lead you down a path. Okay, so when I offset this curve, and we're just going to use offset curve. Oops. I'm going to use offset curve, and I'm going to put in the thickness of the material. So let's say we're going to use 3 mil plywood. Yeah. If I plug 3 millimeters into the distance, what's going on here? And we need to make sure that this is all happening on the XY plane. So we're going to plug that into the P of the plane. What is going on here? This is crazy. I've never seen it do this. Okay, that might be a bug in the new Grasshopper. Let's try offset curve loose. So there's two different offsets. We'll use offset curve loose just to see if that works. So there's the curve, there's the distance, and there's the plane. And that doesn't seem to work at all. This is crazy. Sorry. My bad. 3 is just a huge number. It's just huge. So, my bad. So, okay, it's working. It is working. It's working. So, so we want to use offset curve. We don't need this project. I just set it to 3, and I thought this was offsetting to there, and then I thought this one was offsetting there, and I was like, no, that doesn't work as an offset. But it's just what I'm actually seeing is the offset of the ones next door. Okay, it is working. There's nothing wrong with it. Okay, so we want to offset, but okay, this is the problem. If this is a center line, and let's say I want to use 0.5 mil plywood, so there's the 0.5. Have I actually defined a center line, or have I defined the slot needs to go in equal directions on either side of the line, right? So I actually need a line, like if I wanted a 0.5 mil slot, I needed actually to go to halfway and halfway. Maybe what I'll do is I'll script it just to show you. So instead of giving it 0.5, what we're going to do is we're going to write an expression, a maths expression, where we go x divided by 2. Okay? So any number that goes into x gets divided by 2. We've all done expressions. So 0.5 is going to come out as 0.25, and that's going to give us half the distance. If we then create another offset curve, and we use a similar expression, but we put in a negative x instead of just x, then when we put in the number 0.5, it will center on our center line. Okay. Cool. Okay. So there's a few more issues. So if I were to just close these off, so for example, we can do that quickly by putting a loft at the end of our offsets, and then just getting a curve, converting our loft into a curve is going to turn that into just the boundary curve of it. If I were to just try and quickly cut this out in the laser cutter, it's not gonna cut to the edge, right? Because the center line goes to a certain point, but when you offset it, it doesn't extend out to the edge. Does that make sense? Okay. So what we need to do is just make sure that our lines are extended to a certain point, and we can do that. We'll need to do that before the shatter. So we can go extend curve, plug our center lines into that, and then all we need is a slider to go into both the beginning and end of the extension. So you can see here, you can see this line at set to 0, it's got 0 extension, and as I edge it out, it gets longer on both sides. So if I then plug that into my shatter, that'll guarantee that the slots go like they exceed the geometry. Yeah. So set to 0, our lines are go to the edge at the center, and then set as we extend it, it overlaps, right? It's at this point that we could actually laser cut these, right? Like we could clean these up. Like if we hide the center line, we could clean this up, but if I laser cut it, would it work? Like, would the slots work? Yeah. Like, it doesn't technically need to be clean to laser cut. It works. Yeah? So all we need to do now is we need to copy this to the other side, to the other orientation. Okay? So what I'm going to do first is we're going to copy this. Shall we, to avoid absolute confusion, I'm going to delete the other direction, like so, okay? And we're going to start the other direction again by copying this whole script, okay? So we're going to grab all of this up to basically the plane. We're going to copy it, and we just need to basically change the inputs as they go in. So our B-rep is the same, but our plane is different. We need to count the planes, and the section planes are different. Okay, hang on. What's the easiest way to solve this? The easiest way to solve this is with a cluster. Okay, so before we make the cluster, we need to define the inputs that go in the cluster, okay? So, this plane here, we're going to create, guys, I'm going to grab these things called geometry parameters, and if I'm ever using data, I'm going to grab a data parameter, okay? And what we're going to do is just use these to create a nice clean cluster. Okay, so the geometry, I'm just going to copy that, and we're going to rename that. So you can right click the parameter, and we're going to rename this plywood plane. Ply plane. If we right click it and we select this little paint bucket, it'll give you the text of the element instead of the icon. So we can see that I've written ply plane. Yeah. So we then hold Control Shift, and we're going to drag the XY plane out into the ply plane and connect ply plane back up. So it's working again. So now we're running through this ply plane parameter. Then we're going to copy geometry again. I'm going to rename this B-rep So this is the B-rep that we're cutting the section through. So that plugs in there. We're going to copy geometry a third time. And this is now the slot planes. Slot. Yeah, this is just going to be setting the inputs for the cluster, making it a bit like I've seen you guys writing comments. This helps you, like labeling things helps. Mind you, I rarely label things at work, but and you'll hear a lot of people complain about me saying that. I can show you one of my scripts later if you want. So that's where my slot planes go. And what that should have done is it should have defined what we would consider to be all the parameters required. But there's one other parameter that changes in the other side, and that is the side of the side that we pick. So you know how we've shattered our curves here into two, and we're picking the bottom ones for this orientation. Which ones do you think we should be picking for the other orientation? Right. So that means this index here in the list item, which we have currently set to 0, which needs to be 1 in the other side. So for that cluster, that'll need a different variable. So what we're going to do is we're going to use this 0 as another input. We're going to grab the data, and we're going to say slot position. And we're going to use 0 as the slot position for that. Okay. Now, the output of our cluster needs to be the curves for the slots and the curves for the elements that make up the shape. So what we're going to do is we're going to grab them. So these are the curves of the panels, and we're going to call them, I don't know, shape. And important thing with this is we need to copy this twice. So shape needs to go into itself twice. And we will also get the geometry output of the slot. And we need to copy that, have 2 of it. And then what we need to do is select everything but the very last output. So these 2 slots, we don't want to, the slot and the shape, we don't want to select that. But we want to select all the way back to these named elements. So slot position, slot planes, ply plane, and B-rep. So we want everything in there that's selected. We're going to turn that into a cluster by clicking the middle button and selecting the box, the cluster. So that's now compressed that all into a single component. So then we can just copy and paste that. I understand that this is, it's getting complicated, but bear with me. You guys are doing all right. Copy and paste that. So our B-rep doesn't change. All that changes is that we're using the XZ plane now as the ply plane. We're using the YZ plane as the slot planes. We'll just hide this. And you can see here the slots are still on the bottom. So to make them on the top, we just need to change this 0 to a 1, and that's now moved them to the top. Okay? And another problem is that I've forgotten that we also need to change these sliders. So we need control of them. So we'll just put 2 little X and N sliders in the cluster. And by the way, clusters organize their inputs based on their location in the script. My bad. Where am I going? Here. Sorry about this. So if I put an X and an N input there, and what we do is we'll just drag these down so that they're at the very bottom. Save and close. So that means, come on. That means when I get some sliders here, let's set them to 100, no, 20. Are you okay, Blair? I just sound... That's all I can hear. So if I plug these in here, then that allows me to control those sliders that I was controlling before. Maybe that does need to go to 100, maybe even 300. And then I can use these same sliders in the cluster above. That's where it was pasting. In the X and N there to view the components in the other direction. And we've got a series of slot things that we can laser cut and slot together. Now, there's going to be some difficulty in when you laser cut, because how do you know which piece is which, right? You know, when you pull the stuff out of the laser cutter, it gets a bit confusing. So we can script putting labels on these, but it's 12:30, and you guys can put labels on these manually at the moment. The way to do that is by, in Rhino, you can type text. That'll allow you to write, A or 1, and you can place that, and that'll get etched onto the element as you laser cut it. Really nice, sneaky place to put it, especially if you're using 3mm material, is in the slot zone. Not where the slot's going to fall off, but in the zone where the slots meet each other, because that way when you assemble it, the labels will disappear. You won't be able to see them. Okay? There's a few other little tricks that I do with my own waffles, because you can actually create little clips using this inside the system. So as it assembles, it clips together and you don't need glue. Okay? But a lot of people see this and they think that they don't need glue. They think it's going to friction together. But if you're using a 3mm material and you're cutting a 3mm slot, do you think the laser is infinitely thin? No. So the laser is going to have some thickness. So the slot's actually going to be a little bit bigger than 3mm. So therefore, they're not actually going to friction together. So unless you really want to work on the tolerance and work out exactly what thickness it needs to be to slot together, you're probably going to need glue or a clipping system. Okay? Now, the half an hour that I want to spend is if you want to change the orientation of the planes. Like you want it. You worked it out?
Yeah, rotate.
Yeah. So this will apply to a few of you, because what you'll notice is that you're working on a segment that looks maybe like this, yeah? And the slots are going through it like that, right? And you might want to change the orientation of those slots, yeah? So in our cluster, what we effectively need to do is change the direction of our planes. Okay, so the planes currently are going YZ and XZ. We just need to change that orientation. Okay. What's the easiest way to teach you that in 30 minutes? So you guys have a line. Do you guys have lines that do that? You can extract a line like that from your script. No? I'm guessing that's a no. You got a vector that goes in that direction, right? Or do you have plane? You have a plane that goes through there, right? Because you used the plane. We used a plane to generate the element that goes through the circle, yeah? See, it's all this critical thinking that's the tricky part, isn't it? Okay, so I think the trick at the moment is that we're going to leave this alone, the script. If you can get it up to this point, you're good, okay? If you want to change the way that the planes cut through your geometry, you're going to need to rotate your geometry. Okay? So, if this is my geometry here, which it is, and it is now rotated in a fashion that is maybe not necessarily orthogonal to the system. So you see how it's all screwed up now? Like it's a funky orientation. Then at least we can see these two points. We just need them to help define us rotate the geometry to a rotation relative to x and y. Okay? So, for example, if you've got a geometry element that looks similar to this, that's relatively how it looks, yeah? You've got, as long as you've got a point like this and a point somewhere here that roughly like this, we can use those 2 points to rotate our geometry so that the waffle works for you, okay? Like it makes it orthogonal to the geometry. So to do that, we just need to take those 2 points, and this is slightly more critical thinking than what, but effectively, I'm not going to tell you exactly which points these are. You have to work them out for yourself, okay? But the first point is going to be the point that we need to rotate on, or like it's one of the points. The second point will be this end point here. What we need to do is generate an XY plane at one of the points. We need to generate a vector 2-point between the 2 points. We then can use this thing called a line plane. What it does is when you give it a plane and give it a direction, it'll rotate the plane so the x direction points in that vector. And the really cool thing about that, apart from being very useful a lot, is that it also gives us the angle that it's rotated by. So if we get that angle, we can actually use that to transform and rotate our geometry. So if we were to take our geometry, rotate it by the angle, but the angle needs to be negative, so we can grab the negative by either using an expression or getting a negative x function. That'll rotate it to the orientation that we need for it to then plug into our 2 clusters and be orthogonal. Okay? So we just need 2 points to define where we want it to be orthogonal. We rotate a plane, get the inverse of that angle, and rotate our geometry back, and it should be the right orientation. Okay? Now, some of you, like Corky, you are seeing geometry when it cuts through everything's working except for this one point, right?
I got lost.
You got lost. Okay. Some of you might see geometry like this. Is that right? So the reason that is because when we've taken our surface, your B-rep that was looking a lot like this, right, and we've extruded it. We've extruded up, yeah? So if we were to extrude this extruding up would produce, hang on, it might do something more like this. Extruding up would produce that, yeah? And that's where you're getting that intersection as it cuts like so. Okay? So the way to solve that is difficult. As I've said,
I baked the shape into Rhino and the offset.
let me just, yeah, that's one way of doing it, but let's avoid that. One way of doing it is instead of adding an extrude at this B-rep joint, and this really only applies to those people who might have geometry that curves back on in the Z plane. Instead of having the extrude at the B-rep joint, you can actually you can just slice through the surfacing, not like the infinitely thin surface, not the thick surface, and then in the cluster, once you've created this particular intersection through that infinitely thin plane, we can offset that. Not offset it. We can extrude it up. Oh no, that's still going to cause you a problem, isn't it? We can offset it. So we can put a offset curve, give that a distance that will give it a thickness, then create a loft between the inner and outer curves. Please work. Why has it not worked? But the critical thing here is you really need to make sure that these are simplified. And once they're simplified, that'll start giving it thickness. It gets really tricky. You also need to make sure the plane that goes into it is like we're using the plane that we're using to section needs to also go into the offset, but also make sure that's grafted. So you can right click and graft, and that'll make sure that it all goes in the right direction. Okay, this is purely because you've got this curve doubling back on itself. Okay, what it might be worth doing right now for those people who are using the sports hall is to take just one of these elements actually it doesn't do that, does it? It does this. Just take one of them, pick the top one, and just work on that one for now. Okay? If you don't, you're more than welcome to do this system as well. See if it works. But the benefit of this particular scripting environment is if it doesn't work for the full system, you can just go and get one of the top ones, and you should be able to plug that in and it will work. Okay? Does that make sense, Sarah? Ish. Cool? So one of the actually with sort of comments that way that I say things I'm not really in trouble. Yes. I'm gonna try.
How about that CNC milling?
What about do you have to CNC mill this?